I was about to say.
Whoops.
Like, no, it's happening.
Okay. Oh gosh, time to start. I haven't even started attendance yet. Sorry. Okay, let's see. Robbie. Wait, wrong section. Sorry. Sarah B. Yep. Claire. Matt. Luke. Yep. Jaden. Yep. Emma. Liza. Yes. It's easy when y'all sit right next to each other. Stuart. Ethan. Manya. Yeah, y'all are right next to each other too. Olivia. Kashal. Diego. Darwin. Yep. Sean. Yep. Jules. Doa. Look at this, all these people right next to each other. Matthew, never noticed before. Colin. Emily. Yep. Rennick. Sarah T. McKenna. And several people just came in. Emma. Oh, nice space. Okay. And let's see, Stuart. Who else just came in whose name I didn't get down? Anybody? Missing Claire, Matt, Kashal, Matthew. Got everybody else. Okay. Sorry for the late start. Okay, so last time we were talking about triple integrals. And let me just remind you what the basic deal is here. So we've talked about doing accumulations, what I like to call accumulations, where stuff adds up over an area, right? And so you might have mass distributed over an area, or you can think of volume actually as being a summation of volumes, little French fries, that are stacked up over an area. So we can think of volume as accumulating over an area. But sometimes the accumulation you're interested in is unavoidably over a three-dimensional region, right? So for example, if you're trying to compute the mass in a solid, and if density is just a wildly non-constant function of all three variables, you can't, you can't just say, oh, let's look at a French fry, because the density at different points in that French fry are different. And so again, you have a problem that you can't immediately answer. So what we did is say, well, we just need to come up with a way to generalize the idea of a Riemann sum to three dimensions. In other words, instead of chopping up an interval, instead of chopping up an area. Oh, I knew I was, okay, yeah, this mask is harder to talk in. We need to chop up the actual three-dimensional box itself. Right? If you chop up a three-dimensional solid, you get a bunch of little sub boxes like this. And the details to be worked out. I mean, I need to be able to talk about where they are. So I need to define their coordinates, which means I need to chop up this interval from E to F, right? Not A to B, C to D, but E to F. And yeah, details, sure, fine. That's just to make it precise what we're doing. But the big takeaway is that I can talk about doing a chop it up, add it up strategy on a three-dimensional thing. And yeah, details. Right. So since we don't need most of those details most of the time, we're just going to label this. We're going to call it a triple integral. We're going to use this notation, and then start relating it to applications. So for example, as we've sort of already alluded, how much mass is there in some three-dimensional region where density is known? Well, and I'm going to zoom in here so I can see better. The total mass is the sum of the little pieces of mass that you get when you chop it up into little pieces. So as I like to say, mass accumulates. Right? Okay. Secondly, on each little piece, we have a relatively easy problem. The amount of mass in a little piece is mass per unit volume times volume, right? No tricky curves on that argument. That's a real simple case to make there. Okay, how are we doing? Is everybody happy? All right. Okay, quick reminder. The book goes a little deeper than I do here in the notes in their definition of a triple integral, and their Riemann sum is a more sophisticated thing than this. They use irregular partitions as opposed to the regular partitions that I'm using. They use arbitrary test points instead of the notationally most convenient. You just pick the upper right hand corner like I do here. And just like with double integrals, for the continuous functions that we'll be dealing with in this course, well, and even if not continuous, the piecewise continuous at least functions that we'll be dealing with, it makes no difference in terms of what you're going to get. And so why bother? So we're not going to worry about that. Now, I do want to recognize for non-continuous functions, big problem. And the way the book does it is absolutely essential. That's not what we're doing in this class. Okay. Oh man, this mask is making me appreciate my other mask. It's hard to breathe here. So thanks for your patience, me trying to breathe air here. Okay, so let me warn y'all about a point of view of how to visualize integrals. We've already talked about this before, to the question of how should I visualize a single variable integral. And what everybody does, or everybody is shown as the primary point of view in a single variable calculus class is, well, it's area under a curve. Which, okay, sure, you can compute area under a curve with this integral, and that's nice. And it is something you can draw a picture of, and the picture is nice. The picture is on a two-dimensional piece of paper, which we have two-dimensional paper. The graph itself is a curve that is one-dimensional, which is perfect for our one-dimensional pens. So, I mean, it's really a nice point of view in that setting. And then there's this other application that people kind of mention as, well, I suppose you could think of this as, the mass of a rod, because you can think of this integrand as representing density. You can think of, in other words, each one of these as representing a little bitty piece of mass. It's how much mass is in each little slice as you slice it. Okay. All right. And y'all heard me say, I think this is a better point of view, ultimately, in terms of how you visualize an integral, AKA a Riemann sum. And we are now at a point where I can show you yet another reason that I'm a little bit sort of bearish on the area under a curve point of view, and I'm much more of a fan of this. Let's just kind of follow the pattern and think about what happens with double integrals. Well, double integrals, yeah, you can think of it as volume under a surface. And yes, we have done things with volume under a surface, and it's actually been kind of helpful to us in making certain connections. But you can also think of a double integral as representing a mass accumulated over a two-dimensional region. Okay. So here's where it gets interesting. How are we going to visualize triple integrals? If you're going to use a two-dimensional picture to understand a one-dimensional integral, if you're going to use a three-dimensional picture to understand a two-dimensional integral, well, what are you going to do to understand a three-dimensional integral? You're going to use a four-dimensional picture? I mean, if you were to follow this pattern, what this would have to be the analogous pattern, the analogous interpretation for what our now triple integrals are, would be a four-dimensional picture. And that's really not helpful, right? You can't draw it, and you can't really, and I mean, best case, you can fake your way into psychologically convincing yourself you can visualize it, but you can't actually visualize it. Okay, so on the other hand, notice that this mass point of view goes through just fine, and in fact, arguably even better in 3 dimensions. Here, one-dimensional integral, mass of a one-dimensional rod. Two-dimensional integral, mass of a two-dimensional surface or sheet. What's a triple integral? It's a mass of a three-dimensional thing. Again, arguably easier than these above, because here we're viewing density as mass per unit volume, which is the definition of density that we all learned in middle school science class. Right? It's the most common notion of density out there. So this is a great pattern here. That works fine. Okay, so now let me warn you about one other thing. What a lot of students will do in this situation is they're sort of already like, look, this is how I think of single variable integrals. I'm sorry, I'm stuck. That's just the way I have it. You know, I've got too much water under the bridge thinking of it this way. And double integrals, well, for the last several weeks, I've been visualizing double integrals this way. What am I going to do with triple integrals? I guess I'll visualize triple integrals this way. And not that you can't, but you see the problem is now you've got two fairly similar looking pictures helping you visualize two very different mathematical objects. And that's confusing. It's really confusing. And I think that's going to lead to you know, sort of unavoidable problems. So I want to encourage you, if you feel like you're in this situation where, you know, if you sort of hang your hat on visualizing single variable and double integrals in terms of graphs, this is yet another reason to try to switch over, right, to thinking about single variable integrals in terms of mass of a rod, double integrals in terms of mass of a region. Think of an integral, again, as an accumulation of stuff. Please try not to think of integrals as we're computing a geometric thing, right? Again, unsustainable pattern. Okay, so integrals, try to think of it as the accumulation of stuff. All right. Okay, pause for questions. Everybody with me? Okay. All righty. Yeah, so, okay, now we can't use graphs to make various clever arguments like we did in the case of double integrals. And you know, again, full confession. I mean, when we were dealing with double integrals, viewing the double integral as a way to compute volume under a surface was nice. It allowed us to deal with the difference between double integrals and iterated integrals and to connect them, right? We did that with a volume argument. That was nice. We can't do that for triple integrals. So I'm not going to be able to give you an argument claiming what I'm about to claim, but I am going to claim it and just assert in this theorem that I'm not going to prove that triple integrals can be computed with iterated integrals. And I think it's a highly plausible claim, right? Because, you know, patterns and all that. So again, I think it's pretty believable, and I'm just going to leave it at that. And if this were a more mathematical class, then we'd prove it. And there are ways to do it that don't involve 4 dimensions. There's more algebraically heavy ways to do it. That way, again, we don't need to wade into that. Also, I'm going to claim that no matter what order you do your differentials on specifically, this is for a rectangular box, you get the same answer either way. There are now 6 different ways to order your differentials. You know, 3 factorial, right? So, you know, you have more choices, which is a good thing, but it's also a bad thing because you have more decisions to make, arguably, right? So anyway, but they all will give you the same answer. Okay. And so we end up with the same, ultimately, 3-step process for answering an application question. It's just the exact morally identical process that we just saw with double integrals. Whatever your application is, step 1, write it as a Riemann sum, aka triple integral. Okay. Step 2, you're going to rewrite that triple integral as an iterated integral. And then step 3, you're going to compute that iterated integral with the fundamental theorem. Okay, is that cool? Believable, I should say. I mean, is everybody, I'm making assertions here that I haven't proved or fleshed out at this point. Okay. All right. And let me just point out while we're here, you know, this is where volume would have been had there been a version of volume that I could have fit onto this picture. But again, it's not something I can, I mean, there's a 4-dimensional thing there that I can't sort of do anything with. So obviously I can't say, oh, I want to compute the mass of a 3-dimensional solid. Yeah, that's equal to this 4-dimensional thing that I don't understand. That's obviously not an argument. Yeah. And I'll further claim that you can't make a direct argument for the same reasons as with double integrals. You can't make a direct argument, for example, of why the amount of work that it takes to accomplish a certain task must be an iterated integral, because you've got a lot of square peg round hole problems. You've got, you know, eventually you'll have mass per unit volume somewhere in your argument that you'll be multiplying by length. And again, that's not a thing. I don't know what that is. You're making an argument based on objects that you haven't explained what they are or how they behave. And again, it just doesn't hold water. So you can't make sure not to make that mistake either. You have to make the connection with the triple integral and then turn that into an iterated integral. Okay, let's get our hands dirty and do one. So let's compute the amount of mass in a certain rectangle where density is given. Right. So step 1, I'm going to turn our app. Well, actually, I can be more specific. We're going to turn our application into a triple integral, and this is arguably the easiest part of the problem, because we just make the observation that mass per unit volume times volume gives me mass, and that mass accumulates. The total amount of mass is the sum of what you get when you chop up and get little pieces of mass. So straight interpretation of triple integral set. Second part of the problem, turn your Riemann sum triple integral into an iterated integral. Well, that's easy. From the theorem above. The theorem above says triple integrals are iterated integrals. And luckily, this being a rectangular box, even the bounds are easy. We'll talk about how to deal with non-rectangular domains in a couple minutes. Okay, so phase 1, phase 2. And what remains is just as with double integrals, just kind of plug and chug. We're just going to apply the fundamental theorem down here. And this is there's a little bit more sort of like elbow grease to be exercised here. There's 3 separate individual single variable integrals to be computed. And I am going to go through some of the details here, but nevertheless, it's all plug and chug. Yes.
Why did you choose to order?
Oh, arbitrary. Yeah. So you're wondering why did I order them this way? Doesn't matter. So per this theorem up here, any of the 6 orderings they're all equally good. So I just picked one. Nope. Nope.
We talked about earlier with the double integral.
Yeah.
Would be strategic.
Yeah, sometimes, but in this case, it's not. In this case, it's equally easy in either order. Yeah. So sometimes you just have to pick one for no good reason. Yep. Great question. Anybody else? So let's see here. Let's do the process again. It's just single variable calculus with a couple of asterisks. Do keep in mind, of course, you have to go inside out. So we start with that inside integral. Furthermore, keep in mind that inside integral is where x and y have already been fixed. Right? And so for the purposes of this inside integral, we're going to treat x and y as constants. And so you'll notice here, the x and the y right there. Nothing happens. There's no integration to be done with them. There's no antiderivative, sort of like, do I get a 1/2 x squared? Nope. It's just the x, y is a constant. Treat them like an a and a b, something like that. Right? And so you just carry them on down like constants. And the z antiderivative that I'm doing here, the antiderivative of 2z is z squared. There's where the anti-differentiation happened because z is the variable. Everybody happy? So heads up, right? You got to keep that in mind when you're doing your anti-differentiation. Make sure to keep in mind what's the variable, and also, just as importantly, what's not a variable at that stage. Okay. The other thing to keep in mind, just like with double integrals, yes, these numbers here, oh, I missed. These numbers here are values of that variable. And yes, you gotta, those are the values that you plug in, and we write down the little bracket and everything, right? But again, I urge you to actually indicate specifically which variable it is that you're plugging in for there. Because otherwise, you could well, accidentally plug in for the wrong variable, in addition to the right variable, perhaps. But it's just easy to get confused when you're in that process of plugging in. So, costs you a second or two to write that little thing down, and it's a nice little insurance policy against oopses. Okay. All right. Everything else is single variable calculus. So make sure you can do all your single variable calculus stuff like we talked about before. What do you think? Everybody good? All right. Okay, so now, what do you do with non-rectangular domains? What did we do with double integrals for non-rectangular domains? Well, we made a volume slicing argument. And obviously we can't do the 4-dimensional analog of that in this case. So again, I'm going to have to make some assertions here that it works out in a highly analogous way. And we're going to go through and do a bunch of examples. And I've got several tips and tricks that I think make them go down easier. But we're going to have to just kind of take certain things on faith for just because of the reality. So here's the big picture of the process. And I want you to notice in this process that this is actually a lot like how the double integrals process works. Slice it perpendicular to one of the axes. Identify the bounds based on where the first and last slices are. And once you know those bounds, you then fix one of those slices. Focus all your attention just on that now selected fixed slice, right? And repeat. Move to the next most inside variable. So again, this is an outside in process. And let's see what that looks like now in the 3-dimensional case. Here it is. Suppose we've got some big, 3-dimensional solid here. That's our domain for an integral. Again, let's not worry about phase 1 and phase 3. What am I computing here? Don't worry about it. We'll deal with that as situations arise. Right now, I just want to talk about, for whatever reason, if I want to compute a triple integral on this domain, how do I turn it into an iterated? Okay, so slicing up, no particular reason. I'm going to do my X slicing first. X slices kind of all look like this, or kind of generally roundish slices. That's the slice at, this value of X right there, perhaps. And you will notice that you get similar looking slices at sort of different places. Like if you come over to, just for visual convenience, I'll use blue. So some other value of X over here. There's going to be a different slice back there. Okay. So this being what those slices look like, where's the first one? Where's the last one? Well, we're going to identify where the first and last ones are by with that first slice is going to be where, it's that slice way in the very back where the slice just hits just a single point. And that point, whatever its X coordinate is, that's your lower bound for your X integral. Likewise, your last slice is going to be over here on the front side, where the slice perpendicular to the x-axis just barely side swipes the front end of this lump, and whatever the x coordinate of that is, that'll be your upper bound for your x integral. So notice we've got x on the outside. Notice I'm using the same language outside as opposed to first, because again, that's ambiguous. And my bounds, as we argued from the picture here, from x1 to x2. Everybody with me? All right. All right, now I have a mess to clean up, get rid of my mess. Okay, we're going to focus our attention now on that one single value of x. In other words, we're going to look at this single x slice there. And all the rest of what we're going to do is going to be focused on this one single slice. Let me remind you, up here, we sliced orthogonal to the x-axis. We identified the bounds. Now we have fixed a slice, and everything that we do going forward will be on this slice. And don't worry about what's happening over here. Do I need to worry about that point over there? Don't worry about it. You will get it for a different value of x than the one we happen to be looking at as our for example. I mean, it is on one of the x slices. So, but we want to know what's happening on individual slices and how that varies on x. So we're fixing a value of x and focusing on just that value of x. Okay. And now, next step. We repeat. Slice orthogonal to another coordinate axis, identify the bounds based on the first and last slices, and then etc. Okay, so on this x slice, let's see here, I'll use blue, I guess. On this x slice, what do slices perpendicular to the y axis look like? By the way, why am I choosing the y-axis for my second differential? It doesn't matter, and this is all arbitrary, and so with no particular reason here. There will be motivations when we get specific examples, but right now, doesn't matter. So let's, because I have the picture already drawn, we'll use y for our second slice. Okay, so slices perpendicular to the y-axis look like this. Right, now you've got a geometry task in front of you then. What happens when you take these perpendicular to the y-axis slices and slice up, not the original solid, right, but slice up the x slices that you've already made. So y slices of x slices. And I appeal to your geometric intuition. Those slices are going to look kind of like this right here. Right, so there's going to be, a bunch of slices kind of like that. What do you think? That geometrically Satisfying? Okay, so that being noted, our first slice we will notice is there. And whatever the y coordinate of that point is, that is going to be our lower bound for y. Notice it depends, of course, on x, right? So this is a function of x. Because, I mean, just you can look at the picture, if you take a different value of x, you're going to be looking at a different green cross section, and different green cross sections are going to start and end at different places. Of course they are. Right? So that will be a function of x. It won't be some, closed, value. All right. Let's see the ending point, the last slice, going to be there, which will also have a y coordinate. That will be our upper bound for y. Again, depends on x. Yeah? Everybody good? Okay. So y1 of x to y2 of x. And notice that's what I've got here. From y1 of x to y2 of x. Functions, of course, of x, because x is the variable to the outside. All righty, and then proceeding again. So let me remind you, we've already fixed x. So let's see, so x is fixed. We're looking only at this x slice of our original solid. Now we're going to fix y. And we'll be looking therefore at some y slice of our x slice. On that slice, x and y both now being fixed, we want to look at the range of values of z. And again, don't worry about other points like, what about these points over here? Do I need to think about them as possibly influencing the range of values of z? I will. For other values of y, we'll get there, right? But we want to know how those range of values of z depends on y. And so we're focusing just on that y slice. And, when y changes, we'll get to those points. Okay, there we go. Okay, so that's my lowest z slice. Here's my highest z slice. Notice that these are functions of x and y, as of course, well, they should be. They depend on x because the top point there depends on, well, I mean, which x slice are we looking at? You're gonna get a very different answer for different values of x. And of course, likewise, for different values of y. Okay, yes?
If you were to draw y1 of x, what would it look like on this graph?
Well, you want to draw a graph of y1 as a function of x?
Well, because we said it was the kind of bound of the x slice, but the x slice looks like a circle. So would
well, no. So yeah.
like in the
All right. I got you. So if you want to draw where, how would I identify y1 as a function of x on this picture? My best attempt at that artistically would be, it'd be something kind of like that, right? Because so what we're interested in is looking at each x slice. I want y1 means which point has the lowest value of y on that x slice.
Right. So that would be
something like that.
That would have like a constant z value.
No. Oh, no, not necessarily. I mean, in this, maybe if this is a perfect ellipsoid, then maybe, right? But in general, you can't assume that. No, I mean, in general, if you have imagine some lumpy, super lumpy thing. I mean, sometimes for some slices, let me see if I can draw a picture. For some slices, the cross section might look like that, in which case the lowest value of y is way up there. But if this is where a sufficiently weird solid, right, way over here for low values of x, the cross sections might look like that, in which case the smallest value of y has a different value of z. It just depends on what the nature of whatever your lumpy solid is. So yeah, you can't assume that Z is always going to, that the Z coordinate's always the same. Yeah, right. Great question. Anybody else? Okay. All right. So you end up with an integral like this. Do keep in mind that variables further to the outside, you get to treat as constants. So for example, for the purposes of this y integral, right, as you're doing the y integral, you get to treat x as a constant because it's further to the outside. It means it's already been fixed and set before we even wrote down the y integral. So inside of the blue integral here, you get to treat x as a constant. And likewise, looking at this green integral here, the z integral, we get to that only after both x and y have been fixed. And so you get to treat both x and y as a constant for that inside integral. Get to, have to, take your pick. I like to think of it as get to myself. Yeah. Okay. All right. Just keep in mind we're about to get to an example, but the slicing process, the slicing process is outside to inside, just like with double integrals. We've already observed bounds are functions of variables that are further to the outside. That's just the geometric reality of what the shapes look like. Same pattern that we saw with double integrals. If you want to find a bound, you need to identify what is the point that is the slice that defines that bound. How are you going to understand that point? You're going to understand the point by recognizing it as being on certain surfaces. How are you going to understand said surfaces? Well, you're going to understand that with equations. And so with the equation, the appropriate equation or equations identified, you then solve for the bound that you're actually interested in. Okay, so just like with double integrals, let's get our hands dirty and do one. Start with a tetrahedron. This shape here. Now you'll notice the way that was given. It was given in a bounded by, right? So you've got to understand the various surfaces, and then you have to think how these surfaces intersect and what various different regions do they define, and which of those are actually bounded, right? And I claim if you look at these four planes, there is only one region that's actually bounded, and whose boundary is these four planes, and that's this tetrahedron. Okay, so heads up on the language. Okay, arbitrarily, just to get the ball rolling, we're going to do x on the outside, then y, then z. No particular reason. This is a highly symmetric domain. You can do it in any order you like. I'm going to do this one because this is what we have on the previous page, and it's kind of probably the easiest. Yes.
How do you know that x and y?
Oh, how do I know that this is that plane? Yeah, it's chapter 1. You just have to remember the equation of a plane, normal vector, and all that. So it's a vector. Excuse me. It's a plane whose normal vector is 1, 1, 1. Because that's these coefficients here are 1, 1, and 1. And so, yeah, just kind of visualizing it like that. If you want, another thing you could do is ask, how does this plane intersect that plane? And that's just x plus y equals 1, which is easy to draw. And then you could likewise do it, how does this intersect that plane? And that gives you x plus z is 1, etc. Yeah. Is that cool?
Yeah.
Okay, so here's our solid. X slices. Our first X slice. It's back there. An arbitrary X slice. Something like that. The very last X slice. Going to be right there. So starting and ending values. Again, sometimes you get lucky. It's kind of obvious just from the picture. This first slice is, I can see it right there in the picture. It is part of that plane. I need to know the value of x. Well, it says right there, x is 0, right? So I mean, the first one here is kind of a freebie, and you know, it's nice. Now, less obvious though, this point right here. How do I get the coordinates of that? What is the x coordinate of that point? Well, that point is on certain surfaces. Those surfaces have certain equations. Let's write down those details. That point that I'm interested in, that's going to define my upper bound. Among other things, it's on that plane right there, which has that equation. Now, looking at the picture, I can also see it is also on that plane right there, which has that equation. But I can further see, and gosh, I don't know how I do this without a picture. Gotta love the picture. It is also on that plane, which has that equation. So what I've got here then, 3 equations describing 3 surfaces, all of which are describing, a little bit at a time, this point that I'm trying to understand in, you know, in the interests of getting this bound. So what I've got to do then is solve this trio of equations. Well, here they are. That trio of equations right there, solve for, wait a minute, what am I looking for? I'm looking for x, right? So solve for x in that system of equations, and you get x is 1. And that's where that upper bound 1 comes from. Everybody good? Okay, so notice we followed this pattern up here. To understand a bound, we identified the appropriate point. We identified the corresponding surfaces that it's on. We wrote down the equations of those surfaces, and then we solved to find the relevant bound. Okay. All righty, and now let's do it again. We know our range of values of x. X goes from 0 to 1. We're now going to fix a value of x. Fix some value of x. That means we're going to focus on now this slice where x is, you know, whatever value that is. And I want to know now the range of values of y. Fine. Okay, well, y slices look kind of like that. First slice there, last slice here. The first slice is in the plane y equals 0. So it's kind of a freebie that the lower bound there is going to be 0. So, you know, again, sometimes if you get an easy one to take it, that's nice. The last slice now, though, and let me redraw my picture here. Looking in that x slice, here's the last y slice. What can I say about that point? Well, I know several things about this point, and we need to document now. What do I know about that point? On the one hand, I know what x is. X is fixed. X is known, right? I get to assume x. I'm trying to find my y as a function of x. So I'm going to write, and it feels silly to do this, but I'm going to write x equals x. That's just my sort of algebraic terse shorthand for we know what x is, and I don't need to worry about it. Okay, so x is known. What else do I know about that point? Well, that point, geometrically, I can see that point's on this plane, which has that equation. So I know z is 0. What else do I know about this point? Well, I know that it is on, oh gosh, color choices. It is on this plane right there, which has that equation right there. So trying to understand the upper bound for y comes from that point, which satisfies all of these equations right here. And so within these equations, I need to solve for, reminder, I'm trying to find a bound for y, right? So I need to solve for y, in which I get 1 minus x, and that's where that formula comes from. Everybody see the game? I'm going painstakingly slowly here. I want to make sure everyone sees the process. Now, once you've been around this particular block enough times, yeah, you kind of, okay, you can streamline this, maybe write it down a little faster, but I want to make sure everyone's clear on what the process is that we will be routinely streamlining later. Okay. All right, so we've got our X bounds and our Y bounds. Now X and Y are both fixed. So, we're looking on that X slice. We are now furthermore looking on this Y slice of our X slice. And now on only that slice, forget about everything else. Don't worry about these points over there, these points over here. We'll get them with different values of X and Y, right? So for the moment though, just for the selected arbitrary X and Y, what's the range of values of Z? Well, the starting point for Z is kind of, if you will, down here. The last point for Z is kind of up there. Right, what do I know about these points? Well, I know X and I know Y. Oh, whoops, sorry. Wrong mode. I know X and I know Y, because those are fixed. What else do I know about these points? Well, the lower bound is on that plane, which has that equation. So the lower bound is clearly going to be 0, because solving for Z. Right? The upper bound, you just got to look at where that point is. That point is on this plane, which has this equation. And solving for Z gives me that. It's solving for Z. Okay, everybody follow that process? Same game. It's just that I already know the X and I already know the Y. So I only really had to identify one surface to tell me the last little bit of information that I need to know about the Z bounds, those inside bounds. We solid? All right. Yeah. So while I'm here, I want to take a moment to recognize, can you imagine trying to do this without a picture? Right? I mean, I relied just hugely on having a good picture there. Well, I relied on the picture, and me relying on the picture makes my life easier if the picture is halfway decent. I'll further note this picture that I drew here, that's taking up about a, what's that, about a fourth or a third of the width of the page, probably more like a third of the width of the page. It did get a little cluttered, kind of, you look, then there's a lot going on in that little bit of space right there. And that's a pretty big picture. So it's hard to overdraw your picture. If you want to make a huge picture, I mean, don't take an entire page, right? But don't hesitate to spend half the width of the page on a picture that's nice and spacious and comfortable, where you can see what's going on. Right? Keeping in mind the first version of the picture that you draw might not be perfect, probably won't be perfect. You're probably going to do scratch outs and erases and redraws and stuff like that. So anyway, don't underestimate your picture. It's just terribly important. Okay, moving along. Some generic advice. We're probably not going to have time for the next example today, but you have 6 different orders to choose from. It's very often an important decision, so think it through really carefully. Some 2 bits of advice that carry over from double integrals. Try not to slice through corners. Largely the same reasons, sort of 3-dimensional versions of ultimately the same reasons as for double integrals. And it's geometrically really easy to see happening, right? And saves you effort on writing down what is not going to be convenient later on. And then again, if one variable is more naturally a function of the other variables, put it on the inside. Now that didn't happen here. All of these variables are equally easy to solve for appropriately. But sometimes it will. And if you see that happening, if you see, one of the variables, oh man, much happier solving for this one. I want to think of this as the dependent variable inside. Okay. And then let's see. Last thing, I will point out there is a new point of view that I guess there's a two-dimensional version of this, but it's just not really necessary. But we're really going to use this a lot. Is this idea of projections and how looking at various. Let's see, my example. I'm not going to be able to. Yeah, it's a lot. It's going to turn out that looking at various shadows of your solid can make your life a lot easier if certain facts hold. And that's going to be a valuable trick. And okay, we're out of time. Call it a day. See y'all later. Thanks for coming. And let's see, today's Wednesday. Yeah, so see y'all Friday. Have a good one. Sure thing.